In this video, I'll be working through the question you can see on the screen here from the summer 2025 Cambridge A-Level Maths Mechanics paper 4.2. I'm going to try and show you how to do this question and not just the solution. So definitely pause and rewatch certain parts if you need to. If you're looking for a different question from this paper or a different paper entirely, check out the description below. You should be able to find a playlist there or have a look around on my channel. Okay, let's get into the maths.
In question 5, they give us this drawing and they give us lots of information about this system. Ultimately, we have three balls, three objects, A, B, and C. They weigh 3 kilos, 6 kilos, and 5 kilos. They're attached together with strings that go around these pulleys here. This first plane is rough. That means it's going to have friction. This second plane is smooth, and this guy's just dangling off the air. They tell us that everything is held in one place. It's all not moving, and then it's released. And they tell us everything, this one falls down. Everything that moves to the right, this moves up. And nothing touches any of the pulleys, nothing like that. That's the system they've set up, and they ask us to find the tension in all of these strings. It's a complicated looking question. It's not nearly as hard as it looks. Let me draw the forces involved in each of them. We'll do it for each ball here. So for example, these olive letters, A, B, C. For this guy here, there is a gravitational force going down this way. Remember, this ball is going to move up the hill. If this falls down, this is going to move up the hill. That means there's going to be some sort of frictional force pushing against it. I'll call that F1 for the moment. There's going to be a normal force, regular force, a reactionary force, I should say, coming off this way. So this gravity, we can write that in. That's just 30 because it's 3 kilos. 3 times 10 is 30 newtons here. These are all the forces acting on A. For B, we'll do something similar. For B, there is a gravitational force of 40 newtons coming down. A reactionary force, we'll call this R1 or 2. This moves this way, but there's no frictional force involved in this guy because it's not a rough plane, so there's no friction involved there. So I'm leaving out one on the first one here. We have a tension, a T. We'll call this T1, and this guy we have a tension going this way. We'll call that T1 as well because these are the same string. This tension must equal this tension down here. There's another string, though, coming out this way. We'll call this one T2, and that's all the forces acting on B. And finally, C, I'll move it all the way over here. We have a gravitational force pushing it down, 50 newtons, and we have tension in the string, T2, coming back up. There's not many forces acting on this guy. There's no friction. There's no reactionary force from the ground. It's as simple as that. So they're asking us to solve the tensions. The answer is nearly here. If this was an equilibrium, the tension would equal 50. It's not an equilibrium, though. This guy is ultimately moving down. I can't remember the number. Acceleration of 2 meters per second squared. That's ultimately here. This guy, he's moving to the right, the same, 2 meters per second squared. And this guy, I guess, is moving up the hill at 2 meters per second squared. Forget about these for the moment. This one's the nice and easy one. That means the overall forces involved here equals F equals ma. Remember we know this guy's going down, so the overall force must be pushing it down. So 50 take away T2 must be the total forces on this, and the total forces must equal the mass, which is 5, times the acceleration, which is 2. So rearrange this, we get T2 is equal 40 newtons. So we're finished for half of the answer. And that's why there's only 3 marks for this. Really, if you set it out like this, it should have been an easy enough question. T2 is this. Because very similarly, this one here, the reactionary force is equal 40. We can say that straight away because it's not jumping up or down off the plane. These two, they're not quite equal. It's moving to the right. We would get T2 take away T1 should equal the mass times the acceleration. So it should equal 4 times 2. Again, here we now know this is 40. Take away T1 equals 8. Rearrange this, T1, take away that. We get T1 is equal 32 newtons. Not much maths. If you'd set up the question correctly, the maths was quite straightforward. There are your two answers for part A. The tension in the first string is 32. The tension in the second one is 40.
If you are finding my videos useful and would like to help the channel out, on top of liking and subscribing, probably the best thing you could do is to tell other people doing the exam about my channel. Maybe you could share this video in a class WhatsApp group. Then if you feel I've really deserved it and you would like to buy me a coffee, you could become a member on YouTube or on Patreon. You should find links to that in the description below.
We have ignored this first diagram, but in part B, we need to use that. They ask us to find the coefficient of friction between A and the inclined plane. So we're in this area over here. So first of all, let's fill in some numbers that we know. Let's see, T1 is now 32. They ask us about the coefficient of friction. So it's this friction here. Let me even rub out the friction here. Friction is actually coefficient of friction times or 1 in this case. So everything we need is here, I think. Let's draw this again over here. We'll get 32 going this way. We'll break up this 30. So have a think of what angle is in here. This angle here is 30. So this angle is 60. This angle down here is 30. The opposite goes that way. So this force is, let's see, what's the force? 30 sine 30. And this force down here is 30 cosine 30. And then there's another force here of mu times or. But remember what or1 is. Or1 must equal this. Again, this guy's not jumping up or down. So this number must equal this one. So it must be mu times or1, which is mu times 30 cosine 30. Bit of a mess there. Hopefully you followed along with what I did there. The same thing we did here earlier. We know the acceleration of this whole system. So if we know all the forces on this system, they must go up. They must be pulling this guy up. So the forces in this system must be 32. Take away 30 times sine 30. That's 15. Sine 30 is 1 over 2. Take away mu times 30 times cosine 30 is the square root of 3 over 2. And all of this must equal the mass times the acceleration. So it must equal 6. We just need to rearrange this. Let's turn this into 17. Let me rearrange this as mu is equal, 6 minus 17 divided by, the 2 goes in there. So divided by 15 times square root of 3. That'd be a minus mu still. Clean this up. Let's change this to a plus, that to a minus. That's 11 divided by 15 over square root of 3. But they probably want that in decimal places. That comes out at 0.423, at least to 3 significant figures. So that's the answer for part B. Now, it's already been a long question. I think part A was 3 marks, part B was 4 marks. But there's still more to come. We're going to get 5 marks for part C, and it probably is the hardest part of it. We have the same system. What they tell us happens is once this system's released, remember, this is going to move down. It's going to pull this way. It's going to pull this guy up the hill. When it's released, 1.5 seconds later, we're going to cut this string. And basically, that's it. We're going to cut this string. What happens next? And that's something to really think about, because I think a lot of students probably mess that up. They then ask the question is, how far does A travel from the time it was released? I think what a lot of students messes up here is they think of A being pulled up the hill, which it is. It's being pulled up the hill. They think of the string being cut, which it does. And they think, what happens, A? And I think a lot of students think, well, it just falls. You cut the string, it falls. What you're forgetting here and what you need to know for this question is, let me draw this again. A starts here. It gets pulled up the hill. Indeed it does. It gets pulled up the hill to here after 1.5 seconds. But when you cut the string, it's traveling at a speed now. It was accelerating up the hill. It wasn't going at a constant speed. It was accelerating up the hill. It has a speed in it. It's going up here at a certain speed. When you cut the string, it's going to stay going up the hill. Gravity's going to try and push it down, yes, but it's going to take a little time. So it's going to make a little more of a distance. I don't know, maybe a lot more. I really don't know. Well, I do. I can check the numbers, but we're going to find out now together. That's what we have to do. We have to find this distance and this distance. Both are sort of different questions, indeed. We can use, I'll use the equation of motion because we're just talking about distance. We're going to add in speeds. We're going to talk about accelerations here. But I do want to point out that, for example, we know the acceleration of this guy at the first part. I like to use integration and differentiation. I won't do it because I think students don't like it. This system, we have A is equal to, I could just straight away say V is equal to t plus initial speed, which was 0. And S is equal to t squared, divided by 2, so that cancel out, plus some initial distance. So I can answer this quite quickly with integration. I just want to point that out. I like pointing that out, but I know a lot of students don't. Right, this first system here, we know A is equal to 2. We know T is equal to a half. We know U, the initial speed, is equal to 0. Which equation of motion will we use for that? I guess we could find V. V should be quite easy. It's U plus A times T. So the final speed in this system is 3. That's useful. We wanted S though. Which one will have S? Let's have a look. S is equal to U plus V. That's 3 divided by 2. So that's 3 over 2 multiplied by time. That's also 3 over 2. So it's equal to 9 over 4. That's the distance traveled between the first part and the second part. Where it gets a lot more interesting is figuring out this second part, because what do we know about that? We know the initial speed, I guess, is the final speed of this one. So it's 3. So it's traveling up the hill. What's A? It's not going to be 2 anymore. We cut the string. Gravity is going to be pushing it down, but only down the hill against friction. So we're going to have to think about that one. Do we know anything else? No, we don't know anything else. So that's what we're going to have to work on here. We're going to have to figure out what the acceleration is in the second system, because we had that in the previous. We have drawings for that. So if I draw this out, we know it's 30 newtons down. Friction is still, we're going to travel up the hill. Friction's still going to push it down. Friction was mu times R. R is going to be up here. It's the same as previous, except T is missing. So R is going to be the same as it was. It was 30 cosine 30. So that means friction is going to be the same as it was. It's going to be mu, which, what was that previous? Let me write this mu R here. That was, let's think, 11 over 15 square root 3 is what we found. Or is 30 times square root 3 over 2. So this actually cancels in a lot of this. 2 goes into that 15, 15 goes into that. That equals 11. This is 11 newtons going this way. And remember, gravity broke up into 2 parts. 15 and whatever that one is, 30 cosine 30. This was 30 sine 30, so that's 15. So the total forces on this system, let's put it all here, is just a force going down the hill of 11, this part here, 11 plus 15, that's 26. 26. So we can find out the acceleration in this system. The acceleration is 26 must equal mass times acceleration. So that's mass was 3 kilos. A is that. So A must equal 26 over 3 down the hill. So A must equal minus 26 over 3. I said a minute ago we don't know any other. We need 3 of these, so we definitely need one more. I'd forgotten we do know V because they talk about when it comes to a stop. That's what we wanted. I don't think I even said that anywhere. Starts here at a stop. It gets pulled up the hill. It stays traveling up the hill until it's at an instantaneous stop. So we know V is equal 0. So we can fill in anything we want. Ultimately, we want S. I guess we can skip some of the others because we just need... let's see. I'm terrible at these. Like I said, I always use the integration to do this. But there is a formula for here. Let's see. Let's see. V squared is equal U squared plus 2AS. We can use that formula. We know all of these. We know all of this except for S. So if we rearrange this, let me just put it up here. S must equal V squared minus U squared divided by 2A. And that's 0 take away 9 squared. So 3 squared is 9 on top divided by 2 times 26 over 3, or that's a minus there somewhere. Let's see, the 3 can come up here and multiply this guy to 27. So we're left with, should I not have 2 minuses? Oh, I should have had a minus 9 up here. So those minuses cancel. So we get 27 over 52. Had to just stop and check my notes because I did this using the integration method, so I wasn't even sure this is the right answer. This is in fact the right answer. That's the distance from here to here, 27 over 52. This distance was 9 over 4. That's a really hard question, breaking all the... even understanding what to do at the start was hard, and then breaking it up at each part. Add these two numbers together to get your final answer of, I guess, 36 over 13, I see. Forgive me if that's wrong, because the answer I've checked is rounding this off to 3 significant figures. You get 2.77. That's meters. Yes, distance we're talking. Okay, that was quite a hard, long-winded question. I'm not sure I helped too much by how I did it. I jumped around a little too much, so apologies for that. If you have any follow-up questions, let me know in the comments which question you're talking about, A, B, or C, but I'll do my best to get back to you. Thanks for watching and have a great day.